Lecture number 9, Compounds, Formula, Mass, and Representation. So this is the last lecture for Chapter 2. So we've come through, we've talked about what makes up atoms, how those atoms then come together to form compounds, how we name those compounds, whether ionic or covalent. And now we're going to start making the transition from that micro scale, the really small atoms, into the macro scale, what we work with, such as grams. And the first way we're going to do that is we're going to talk about the formula mass, talking about how much those compounds weigh, and then how we can represent those on paper. So this first one, formula mass, the formula mass is the sum of those atomic masses. So we're going to take all the atoms present and the mass of each one of those atoms and add them together. So for example, H2O. The formula mass for that is we're going to take the two hydrogens, which both have a mass of 1.008 AMUs, and add that to the mass of the one oxygen, 16 AMUs. So we get a total mass of 18.016 AMUs. So we look at the mass of the water, it is 18.06 AMUs. Those individual masses, and sum them together so we get this total formula mass. We can do the same thing then with calcium nitrate. Now see we have two nitrates, so we have to account for all those atoms. So we have a total of one calcium, which has a mass of 40.08 AMUs. Two now nitrogens, because each nitrate has one of those nitrogen, there's two of them, so 2 times its mass of nitrogen is 14.00 AMUs. And now we have 6 oxygen. Each nitrate has 3 oxygens, but there are 2 total nitrates, so a total of 6 oxygens. We take 6 times, that's 16.00 AMUs, for a grand total of a formula mass of calcium nitrate to be 164.08. So we're going to take these formulas, either covalent or ionic, figure out how many atoms there are, and then take that number of atoms times their masses, add all those together, we get this formula mass. A couple of different conventions when we talk about these formulas. We've been talking about the molecular formula, and that's the exact number of each element, the smallest unit of the substance. So an ionic compound, like NaCl, that is its molecular formula. For each unit, there's 1 sodium and 1 chlorine. It doesn't really tell us how those are connected, or the CO2, for example, 1 carbon has for every 2 oxygens that's present. But it doesn't tell us how those are related. So we have this other formula, which we'll call the structural formula, which not only tells us what atoms we have, but how those atoms are connected. And finally, we have what we call the empirical formula, which shows the elements present in their simplest whole number of ratios to atoms. Right? We'll see how that, for an ionic compound, those formulas, the molecular formula, is going to be equal to the empirical formula, which may not be the case for those covalent compounds. For example, if we look at water, it has a molecular formula of H2O. That's the smallest whole number ratio between those, so its empirical formula is also H2O. Or we look at chlorine, its molecular formula when it forms an atomic state is Cl2, but its empirical formula for that would just be Cl, so there's a difference. We look at ammonia, NH3 has the same empirical formula. Now if we get into some organic, some larger molecules, we have a compound C6H12. Right? If we look at its simplest whole number ratio, that would be CH2. So the molecular formula and the empirical formula are different. And we can look at a larger molecule, C12H24, which also has the same empirical formula, CH2. So multiple molecules can have the same empirical formula, but they'll only be represented by a single molecular formula. So there's a difference. And we'll then use this distinction to help us go from the amount of atoms that are present to an actual formula in the next chapter. And we're going to represent these. We've always written the molecular formulas as they are here, right? That shows just a shorthand notation of the number of atoms that are present and sort of what order. An example of that structural formula is if we look at H2, it's a hydrogen bound to another hydrogen. H2O, we have an oxygen in the middle surrounded by 2 hydrogens, example. Right? In the lab, we might use a model system, so a three-dimensional model called the ball and stick, where the atoms themselves are represented by balls and the bonds between those are represented by sticks. To give us a more clear idea of what this looks like, we also have the shape fill model or space filling model, which shows us sort of a three-dimensional representation of the space that these take up. Right? So you need to start learning to make that transition between the molecular formula and the structural formula. We'll spend a lot of time throughout the semester and then again next semester making that transition very clear, but just be aware that when we do this representation, there's several ways we can represent these molecules that we've learned to name so far. The next chapter we'll start talking further, explore this idea of going from the microscopic, this atoms, into the macroscopic world that we live in, this grams and volumes that we're familiar with.
Dad, I done did it.